All right, great. So here we're going to look at the conservation of linear momentum. So what we're going to do is we're going to look at objects that are colliding. Objects that are colliding, right? When objects are colliding, let's say we have two trolleys here, whether it's in a shopping mall or whatever it is. Let's say we have trolley number one here. We're going to call this trolley A. And trolley A, let's just say its mass is 615 grams, and it's going to the right at 360 centimeters per second. That is the velocity, right? And this is and then we have another trolley here. We have another trolley here that is stationary. We have trolley number B that is stationary. B of weight, let's just say 620 grams. You know those shopping those grocery trolleys. They're just weird, different weights, different wheels and stuff like that. They act weird. But let's say this one is stationary, and we will call this before. This is before collision, all right? Before collision, and this one comes, and then collides with this. And when they collide, let's say they hook each other, or in physics it's called coalesce. So let's say they coalesce, right? And after collision, let's just say they are joined. You know those trolleys, you can join them, right? So that's exactly what we're showing here. They are joined now. They've coalesced into a single entity. This is 615 grams, this is 620 grams, right? So they've coalesced like that, and they move off at a speed of 180 centimeters per second, like this. And we are going to call this situation after collision. After collision. Cool. So let's do a bit of calculations. So before collision, what was happening before collision? Before collision, we had there was momentum there. Let's calculate the momentum before collision. So it was obviously going to be momentum of A plus momentum of B. I think you can agree. Momentum of B. So momentum of A is going to be mass of A times velocity of A plus momentum of B, which is mass of B times velocity of B. This is equal to, what is mass of A? Mass of A is 615, so it's going to be 0.615, right? Times velocity of A, which is 3.6. Plus mass of B, which is 0.62 times, what is the velocity of B? This thing was stationary before, right? It was stationary before the collision. It was just chilling there. It was chilling. No, it wasn't no movement there. So the velocity was 0. So this falls away. This term falls away. 6.2 times 0 just falls away. So the momentum that was there for the whole system, that was there before collision, is equal to this 615 times 3.6, and that is equal to, okay, it's equal to 2.20 times 2.20 kg meters per second. Perfect. Let's look at the situation after collision. And then after collision, what we are going to see is these things have joined, right? They have coalesced. They are now one entity. It's now one entity, right? So after collision, let's calculate them. So momentum after collision is going to be momentum of both A and B, because now this is now one entity. Momentum of A, both A and B. So this is equal to mass of A plus mass of B times the velocity. Both of them are moving it now. So this is equal to mass of A, which is 0.615, plus mass of B, 0.62, times velocity, which is 1.8. And when you do the calculation, what you actually find is this is 2.20 kg meters per second. But wait a minute. This 2.2 after collision, the momentum after collision, is equal to the momentum that was there before collision. Even though B was stationary, A was moving. Now when they joined, they are they seem like different situations. But that is what is called the conservation of linear momentum. The conservation of linear momentum, it was developed by, you guessed it, Isaac Newton. And so here what we have seen is the collision before and after momentum, the total momentum of the whole system just remained the same. So in the next video, I'm just going to talk about the principle itself, which are without doing the calculations, but you have seen the calculations. Let's talk about the principle in the next video.